Hi, this is an explanation for problem 90 in chapter 12. Problem 90 reads, Susan, whose mass is 68 kilograms, climbs 59 meters to the top of the Cape Hatteras lighthouse. Part A then asks, during the climb, by how much does her potential energy increase? Now, potential energy is derived by delta U equals mass times gravity times height. So we're given these three values, so it should be a pretty simple equation, or calculation. 68 kilograms times 9.8 meters per second squared times 59 meters, we're going to get 39,318 joules. All right, part B then asks, for a typical efficiency of 25%, what metabolic energy does she require to complete the climb? Again, pretty straightforward calculation. E sub m equals energy divided by efficiency. So we have our energy, 39,318 joules divided by 0.025. We get about 157,300 joules, which I've then converted to kilojoules just so it's a smaller number, 157.3 kilojoules. All right, part C then says, when exercising, the body must perspire and use other mechanisms to cool itself to avoid potentially dangerous increases in body temperature. If we assume that Susan doesn't perspire or otherwise cool herself, and all of the lost energy goes into increasing her body temperature, by how much would her body temperature increase during this climb? Okay, so let's break this down. I went ahead and I used 75% left over, so say she was 25% efficient using energy towards actual climbing. That means there's 75% left over going into thermal energy. So 157.3 times 0.75 is approximately 118 kilojoules. Now we can use the equation delta T equals delta Q divided by MC to determine change in temperature. So if we reconvert our kilojoules back into joules, so 118 kilojoules can be 118,000 joules divided by 68 kilograms times 3,400 joules per kilogram per Kelvin, we will get a grand total of 0.51 degrees Celsius increased.